This video is part of the lectures related to the machine dynamics topic. It is the fourth video in the introduction section. This video is going to present and discuss Grashof law for 4-bar mechanisms. By the end of this video, you will be able first to enunciate the Grashof law. You will be able to state the Grashof law for 4-bar mechanisms. You will be able to tell what is the Grashof law for 4-bar linkages. Second, you will be able to predict the behavior of a 4-bar linkage using Grashof condition. Knowing the lengths of bars, knowing which bar is the ground, you will be able to tell if the 4-bar mechanism is a double crank, a double rocker, or crank-rocker linkage. In order to achieve these outcomes, the video will be divided into 3 parts. First, we are going to depict the crank motion and the rocker motion of bars. Actually, the Grashof condition will predict the kinematics of the 4-bar linkage in terms of cranks and rockers. Thus, it is important, in the beginning, be aware of the difference between the crank motion and the rocker motion. In a second part of this video, we are going to enunciate the Grashof law for 4-bar mechanisms. Similar conditions exist in the literature for other mechanisms like slider crank mechanisms, etc. However, here, we will focus only on the case of 4-bar mechanisms. Finally, is the last part. We are going to use the Grashof law in some examples. We are going to apply the Grashof condition to several 4-bar mechanisms, in order to predict the type of motion of the linkage. Also, knowing a desired type of motion, we are going to design a 4-bar mechanism that give that required type of motion. We are going now to start with the first part. We are going to give definitions of a crank motion and a rocker motion. Cranks and rockers, both, are links that have a fixed axis kinematics. They are bars that are connected to the ground through a revolute joint or a rotating kinematic pair. Thus, cranks and rockers are bars that pivot or rotate around the grounded link. Cranks accomplish or complete full revolution motion. They can undergo a 360-degree revolution. There is no limitation on the range of the rotation angle. The crank can have any angle between 0 and 360 degrees. There is no veto on angles. Cranks can rotation on the revolute or pin joint in A without any constraint. While rotating, the end of crank bar B draws a full circle. The extremity of the bar B goes along a circular path. B can go to any point of the circular trajectory. While rotating, the crank bar draws a full circular surface. Rockers, on the opposite, cannot complete a full revolution. Rockers can only undergo a revolution with a limited angle range. There are some angles that are banned to the bar or link. The rocker bars can only go back and forth. They have an oscillatory motion. The rocker's motion is constrained such as they can go beyond a minimum angle. They cannot also go higher than a maximum angle. The extremity of a rocker can only go along an arc of the circle and can complete a full circular trajectory. While rotating, a rocker draws a part of a circular surface. The positions of the rocker draws a sector of a circular surface. Let's move now to the second part and see what tells Grashof law, or Grashof condition. Let first S be the length of the shortest bar. Let L be the length of the longest bar. Let P be the length of the third bar, any bar of the two remaining bars. Let Q be the length of the last or fourth bar. The Grashof condition tells that, if the shortest bar length added to the longest bar length, together, they are lower or equal to the sum of the lengths of the two other links, then at least one link can accomplish a full revolution motion, a 360 degrees rotation. If S plus L is lower or equal to P plus Q, then at least on bar has no angle limitation. It is at least one bar, it can be two bars or all three rotating bars. In this case, the mechanism is called a Grashof 4-bar or a Grashof mechanism. A Grashof 4-bar mechanism has 1, 2, or 3 links that can accomplish full 360-degree rotation. If the Grashof condition is not satisfied, if S plus L is higher than P plus Q, then the mechanism is non-Grashof. In that case, all the links of the mechanism cannot accomplish the full rotation motion. All the bars can only go back and forth. They have an oscillatory rotation motion. Let's focus now on Grashof mechanisms. There is 3 main cases. These cases depend on how the shortest link is positioned relatively to the ground. The first case is when the shortest is the ground. In this inversion, all the bars can undergo a full rotational motion. Thus, the 2 bars that are connected to the ground, the blue and magenta bars, are cranks. The mechanism is called a double crank 4-bar linkage or mechanism. In the second case, the shortest link is not the ground. However, it is directly connected to the ground using a pin kinematic pair. The shortest link is adjacent to the grounded link. In this case, the shortest link a crank. The shortest link can accomplish a full 360-degree rotation. However, the other link connected to the ground, the red link here, can only go back and forth, it is a rocker. The linkage is called a crank rocker 4-bar mechanism. The last case happens when the shortest link is the coupler, is the link opposite to the ground. In this case, the coupler can accomplish a full 360-degree rotation. However, the 2 other bars, the magenta and blue bars, can only go back and forth. These 2 links are then rockers. The mechanism is a Grashof double rocker 4-bar mechanism. When S plus L is higher than P plus Q, when the mechanism is non-Grashof, all the bars have an oscillatory back and forth rotational motion. The bars connected to the ground are rockers. The linkage is also called a double rocker 4-bar non-Grashof mechanism. The difference between a double rocker Grashof and double rocker non-Grashof is in the motion of the coupler. For the double rocker Grashof 4-bar, the coupler can accomplish a full rotation. For the double rocker non-Grashof, the coupler has an oscillatory motion. To work with the Grashof condition, we need first to collect the lengths of bars. We need then to compare the sum of the lengths of the shortest and the longest links with the sum of other two links' lengths. If S plus L is higher than P plus Q, the mechanism is non-Grashof. All non-Grashof mechanisms are double rockers. If S plus L is lower or equal to P plus Q, the mechanism is Grashof. And we need to check if the shortest bar is the ground or not. If the shortest bar is the ground, then the mechanism is a double crank. Then if the shortest bar is the coupler, then it is a double rocker. If not, if the shortest bar is neither the ground nor the coupler, then the mechanism is a crank rocker. Now, we know what Grashof condition tells. We are going then to apply it to some examples. Knowing the bar lengths of some 4-bar mechanisms, we are going to predict if the mechanism is double crank, double rocker, or crank rocker. In the first example, the shortest bar is 5 units of length, the longest bar is the 12 units, the other two bars are 10 and 9 units respectively. The shortest bar is considered as the ground. The shortest and the longest bars, together, make 17 units, where the two others, together, make 19 units. Thus, this mechanism obeys to the Grashof condition. As the shortest link is the ground, then, the mechanism is double crank. Here we depict the motion of the mechanism. The red bar, the input, can complete 360 degrees revolution. It is a crank. The green bar, the output bar, can also accomplish a full rotation. It is a crank as well. Here we show that the extremity of the input bar, the red link, draws a complete circle while rotating. The extremity of the output link, the green, draw a circular path, as well. This confirms that the red and green links are cranks. In this second example, we modified the 4-bar mechanism of the first example, by increasing the length of the shortest bar from 5 units to 8 units. So now the shortest bar is 8 units. The longest bar is 12 units. The two other bars are 9 units and 10 units. Thus, now, the shortest and the longest bar together make 20 units and the others two links together make 19 units. This mechanism breaks the Grashof condition. It is then a non-Grashof mechanism. The green and red links are here rockers. This is a non-Grashof double rocker 4-bar mechanism. This is now a visualization of the double crank non-Grashof mechanism, where the input bar, the red bar, is a rocker. It has an oscillatory back and forth behavior. The output, the green bar, is also a rocker. It can only go back and forth, and cannot complete a full revolution. Here also, the coupler, the magenta bar, cannot complete a full revolution, as it is a non-Grashof mechanism. The extremities of the input and output bar can only draw, each, an arc of a circle. They cannot complete a full circle. Some ranges of angles are banned to the links, because of the linkage's geometry. In this third example, we are going to find the length of the ground of a crank rocker mechanism, if the bar's lengths are 20 cm, 35 cm, 30 cm, and 31 cm. To have a Grashof crank rocker 4-bar mechanism, the coupler is required to be the shortest link. Hence, the coupler should be 20 cm long, as it is the shortest link. Consequently, the ground can be either of the three other links. The ground is then either 30 cm long, 31 cm long, or 35 cm long. In the fourth example, we are going to find the length of the ground of a double crank mechanism, if the three ungrounded bars are 50 cm, 63 cm, and 67 cm long. The mechanism is double crank, thus, the shortest link is the ground. Thus here we are going to find a possible value of S. Finding a possible value of grounded link's length means finding a possible value of S. Also here the mechanism is a double crank, consequently, the Grashof condition is fulfilled here, consequently S plus L should be lower or equal to P plus Q. Here L will be the highest value 67 cm, P and Q can be either of the two other values. For example, we will consider P is equal to 50 cm and Q is equal to 63 cm. Using the Grashof condition, we have S lower or equal to P plus Q minus L. Substituting the numerical values, we will have S lower or equal to 46 cm. Thus, 46 cm is the higher bound of the ground's length. We should also consider the condition that ensures that the four links to be assembled. This will give a lower bound of the shortest and grounded bars. However, this point is out of scope of this video, and disregarded here. The fifth and last example deals with a 6-bar mechanism. We would like to predict the motion of the bar CD. This 6-bar mechanism is compound mechanism. It is a combination of two 4-bar mechanisms. ABCD is a first 4-bar mechanism, CDEF is a second 4-bar mechanism. In order to predict the motion of CD, we are going to separate the two 4-bar mechanisms, and then, applying the Grashof condition to each one. Let's focus first on the 4-bar mechanism ABCD. In this 4-bar mechanism, the shortest link is 7 units, the longest is 13 units and the two others are 8 and 9 units of length each. S plus L here add to 20 units and P plus Q add here to 17 units only. Thus S plus L are higher than L plus Q. ABCD is a non-Grashof 4-bar mechanism. Thus it is double rocker. Thus CD is a rocker. In a second step let's focus on the second 4-bar mechanism, the 4-bar mechanism DCEF. Now S is equal to 7 units, L is equal to 13 units, P is for example equal to 9 and Q is equal to 12 units of length. S and L add to 20 units and P and Q add to 21 units. Thus Grashof condition is fulfilled. DCEF is a Grashof 4-bar mechanism. Moreover, DF, the shortest bar is the ground. Thus, this is a double crank 4-bar mechanism. Thus, DC is a crank. Analyzing the ABCD 4-bar mechanism leads to a rocker CD bar. On the opposite, analyzing the DCEF 4-bar mechanism 5CD a crank. However, the rocker motion of CD leads to a harder constraint on CD motion. The rocker motion prevails on the crank motion. CD is here subjected to the hardest condition. Thus, CD here is a rocker. With this fifth example, we come at the end of this video about Grashof condition. Thanks for watching.